Okay, hello everyone. Thank you for joining me. Now let's get started. So my name is Mal Skoran and I'm a program associate for Green Energy Consumers Alliance. I mostly work on the Drive Green program, which is our electric vehicle discount program. And a lot of the work that I do focuses on consumer education for electric cars. So I'm very excited to be able to talk a little bit more about battery technology today, because batteries really are a crucial part of electric vehicle powertrains and will very heavily influence adoption rates in the next couple of years. So with that, let's get started. So just a couple of webinar logistics to get everyone on the same page. Everyone is muted to avoid background noise. If you hear anything coming from your own microphone, I encourage you to simply mute yourself or turn your microphone off. We will have regular breaks for questions, and feel free to use the chat function in the GoToMeeting to send me questions, and I will try to answer them to the best of my ability. One last thing, this webinar is being recorded, so if you are interested in getting access to these slides in the future or reviewing some of the information that we'll be talking about today, you will be able to do that. So, Green Energy Consumers Alliance is a nonprofit, and our mission is to enable people to make green energy choices in the most cost-effective, practical, and seamless ways possible. And also to advocate for energy policies that benefit the greater good. And we believe electric cars are a crucial part of this mission in several respects. First of all, they've been proven to reduce carbon emissions. When charged on the New England grid, electric cars release about a third of the emissions per mile as a gasoline-powered car. And since there are more renewables being added to the grid every year, the carbon reduction benefits of EVs will only increase. Furthermore, without a tailpipe, electric cars also reduce local air pollution, which will reduce rates of asthma and other respiratory issues, especially in urban areas. So they're a public health tool as well. And finally, electric cars offer an excellent opportunity for consumers because they are cheaper to fuel and maintain. Electricity is cheaper than gasoline, and electric cars are simpler machines, as we'll be talking about in this webinar. So they really do have a lot to offer to consumers. And if you are interested in learning more about some of the benefits of electric cars, I encourage you to visit the Green Energy Consumers Alliance website because we have a lot more information about that as well. So let's get started. This webinar will be taking a deep dive into electric cars, specifically the battery technology of electric cars. So first, we'll be talking a little bit about how batteries work, just a short chemistry lesson to get you prepped for the rest of the webinar. And then we'll be talking about costs. So why electric car batteries are expensive now and why they are getting cheaper very quickly, and why they will continue to get cheaper in the near future. A lot of that has to do with raw materials, so we'll be talking about how these batteries are developed in the lab and how they are scaled up for manufacturing to meet the demand of electric cars all over the world. And then finally, we will just cover some basic tips on how to care for lithium-ion batteries. Which is really important for cars, especially as more and more people transition to owning electric cars. But really, it's advice that can be applied to phones, computers, tablets, any of those devices. So let's get started. Lithium-ion batteries will be the focus of today's webinar, since that's the chemistry that dominates electric car batteries. But in general, batteries all operate on the same principle. So you're using a difference in electrical potential, which is also known as voltage, between two electrodes, one positive and one negative. The voltage drives the flow of electrons, and depending on the direction of that flow, can be used to power an electrical device or be used to store energy in the battery. So we have a diagram here to try and explain how that works in a more physical sense. So the cathode, which is the left side there in that diagram, is the positive side, and that's actually where the lithium is in a lithium-ion battery. There's always oxygen in there too, and some other metals as well, which we'll talk about later. The anode, or the negative side of the battery, is pictured there. It's usually just graphite or carbon. So it's two-dimensional sheets of carbon. And you'll see that the lithium ions actually fit in between those sheets. And again, it's the difference in voltage between those two terminals of the battery that actually allow the battery to operate and store energy. You'll also see the two terminals are connected by some sort of wire. So that is where electricity flows either to charge or discharge. And then there is also a special fluid in between the two terminals of the battery called an electrolyte. An electrolyte forms a bridge between the cathode and the anode, and it allows charged ions to move back and forth between those two places. The key thing to know here is that electrons can't pass through this electrolyte. So instead, they move up through the circuit and allow a flow of electricity to occur. When charging, energy is used to separate the lithium ions from the oxygen in the cathode, and then you store those lithium ions in the negative part of the battery until you attach a load and it's time to discharge. Then the lithium is allowed to flow back to the positive side, and with that, there's a flow of electrons that is the electricity to power the car. So that is the general idea for how batteries work. This particular diagram shows lithium ion, but other chemistries will use other metals. So zinc, silver, copper, those are all really common materials for batteries. But that begs the question. So if there are so many different types of chemistries that are available for batteries, why is it that lithium ion has dominated the electric vehicle market? You're probably familiar with lots of batteries in your everyday life. There are AA's and AAA's, which are known as alkaline batteries, or nickel metal hydride batteries are very common as well for rechargeable devices. For example, my own electric toothbrush uses a nickel metal hydride battery. And of course, there's the lead-acid battery, which is a technology that is already found in cars to power electronics. So why not use any one of these other types of batteries? The reason for that is each different type of chemistry has different properties. And so we really want to be able to choose a battery that has a lot of that meets a lot of the demands that we are asking of them to be able to be appropriate for an electric car. And so you'll see here that in green, lead-acid batteries are pretty cheap, they're easy to recycle, and they're reliable enough to be used in cars of all sorts of temperatures. But they're really not energy dense or power dense, which means that in order to store a certain amount of energy, they take up a lot of space and they're pretty heavy, which is a problem for application in cars. We really need to be able to store a lot of energy without taking up that space or weight. And so the heavier the car is, the less efficient it'll be. And so we want a battery technology that is as lightweight as possible. Not only that, we want the battery to be able to be charged easily, be maintained easily, and not lose a lot of energy while it's charging or discharging, and also have a long lifespan as well. So you'll see that even though chemistries like the lead-acid battery are really common and have some great uses in cars, they're just not good enough to be able to power an electric car completely. Which takes us to lithium-ion technology. which really excels at a lot of the things that we need for a vehicle. Most importantly, they're power dense and energy dense, so they can store the amount of energy that we need to go hundreds of miles without taking up a lot of space or weight. They also last for a really long time, meaning they have a large number of charge and discharge cycles that they can take up. They're easily rechargeable, and they output a consistent voltage. So it doesn't matter if they're at 20% capacity or 80% capacity, they're able to put out a consistent voltage, which is important for the operation of the car. So even though they do have some shortcomings, namely their performance in extreme temperatures, the lack of recycling processes, and cost, which we'll talk a little bit about in this webinar, they really do offer a lot of the things we're looking for in a good battery. So once you decide the lithium-ion is the best battery, there are lots of different types of lithium-ion batteries. So as I mentioned before, the cathode part of the battery, which is that positive part, usually contains a lot of other metals. And those metals can be used to fine-tune the battery's performance to improve it so that we can get the performance that we want out of it. So research in batteries is focused on developing what metals should be in that cathode and in what proportions. And so there are a lot of options here, and depending on the application that you're using the lithium-ion battery for, you will want a different combination of chemistries. It is a difficult job, though, because trying to optimize for one factor usually compromises another. So, for example, if you're trying to improve the energy density of the battery, so trying to get it to store as much energy as possible without adding a lot of space or weight, that can really increase its cost, for example. And so here on the screen, you'll see a mapping of 3 really common lithium-ion battery chemistries and the relative differences between them. So first we have the lithium iron phosphate battery, which you'll see while it lasts a really long time and can output a lot of power quickly, it doesn't have a very energy dense chemistry. So while it would be good for stationary applications, it's not great for putting in a car. In the middle there is NMC, which is nickel, manganese, cobalt, and that is actually the standard for electric cars right now. So you'll see it's pretty well-rounded, it's very energy dense, it has decent lifespan or performance, though it is a little bit more on the expensive side. And then finally, all the way on the right, we have the battery chemistry that is used by Tesla right now, which is the nickel, cobalt, aluminum battery. And they claim that these batteries can charge faster, have better longevity, and also have lower costs as well. And so there are quite a few options that we have for electric cars here. And even within a specific type of chemistry, for example, the nickel, manganese, cobalt battery, depending on how many or how much of each metal is in the battery, that will also affect its performance. So there are quite a lot of factors here to consider. So before I move forward, I will just take a look at some of the questions that we have. So someone asks, are any of the supercapacitor enhanced batteries deployed broadly enough in automotive applications? The Ultra battery was in many stationary storage applications in India when we taught light EV tech there in April. So as far as I know, there are no supercapacitor enhanced batteries available in electric cars right now. In general, as I'll talk a little bit later in the webinar, it can be hard to scale up production of certain batteries in order to meet the demand that is required. So while these batteries may be good for stationary storage, it's possible that they are a little trickier to deploy in electric cars. So I will have to look into that and get back to you. Kate asks, people say there's limited lithium available on the planet. What about that? So we actually will be discussing the raw materials and how these metals are mined in a little bit. So I will have to put a pin in your question for now, Kate. Steve asks, who are the people in the picture? Those people are some folks who bought electric cars through Drive Green and have kindly allowed us to use their photos. You can see the Nissan LEAF in the background. Gary asks, what's the electrolyte in a lithium-ion battery? That's a good question. So it can depend. In a cell phone battery, it's usually a polymer, so something that is gel-like. In electric cars, it's a liquid, and the name of the chemical is escaping me, but it's basically just a liquid that allows ions to pass through. I'll have to double check on the exact material though. Ben asks, what was the scale for safety and longevity? Was a higher safety value safer or more dangerous? So the scale is a relative scale. I'm not exactly sure what the criteria was to make that decision, but a higher safety value means it's more safe, whereas a higher cost value would be more expensive. Yeah, thank you for those questions. All right, and it looks like that was about it, so we can move on. All right, so now that we know a little bit about how these batteries work, let's move on to talking about how batteries affect the cost of an electric car. So upfront cost is one of the biggest barriers towards EV adoption for consumers. Even though there are financial incentives available to help people buy them, the higher sticker price can still discourage people. So we really need to be able to sell EVs at lower prices in order to expect mass adoption. And part of the reason, actually the biggest reason that these cars are so expensive is the battery. So the battery, far and away, is the most complicated and expensive part of an electric car. To drive that point home, I will say an electric powertrain, so the device that actually translates energy into rotation of tires, an electric powertrain only has about 17 moving parts compared to a gasoline-powered car, which can have upwards of 400 moving parts. So in many ways, electric cars are simpler machines than their gas-powered counterparts. But the battery is what makes the entire car much more expensive. So batteries account for a little over a third of the sticker price of a car right now, which is quite a lot. But the good news is they are getting cheaper and very, very quickly. So you'll see in this top graph here, since 2010, battery prices have been dropping precipitously. And compared to the adoption rates that we see in the lower half of the screen, that really is encouraging more people to purchase them. So with a lower sticker price, we're seeing that EVs are expanding beyond this niche market and are entering the mainstream. And so since 2010, battery prices have dropped nearly 85%, and in that time frame, we've gone to from having almost no electric cars on the road to 1.2 million. So really, it's the future of the electric car depends on battery prices. And even since last year in 2018, we've seen about a 21% drop in prices, which is consistent with the trend that we're seeing. But as we know, we can't expect to understand the future by looking at the past. So let's look ahead, because we really want battery prices to come down in order for electric cars to be more affordable. And in order for more people to start considering electric cars, they need to be a comparable sticker price. And in order for that to happen, the target price for battery packs has to be about $100 per kilowatt hour. So at that point, there will be a crossover to where electric cars are actually less expensive to purchase than gasoline-powered cars. Right now, we're at about $139 per kilowatt hour of storage. So we're very, very close, and analysts expect to meet that target as early as 2022, which I probably don't have to remind you, it's just 3 years from now. So for most people, it will be a no-brainer to switch to an electric car at that point, because they'll be cheaper to buy and they're already cheaper to fuel and maintain. And so considering this price drop, people are expecting that by 2025, 30% of new car sales will be electric cars, which right now we're just at 2% of new sales. So that is a huge, huge increase in sales. And so if you are skeptical of this prediction, that's fair. It's extremely aggressive, but it's also really promising that in 2018, these same analysts predicted crossover in price at 2024. And now this year, they've moved that up to 2022. So things are moving fast, but they're moving faster than people are initially anticipating. So if we do consider this prediction to be accurate, we will have to get 8.4 million cars on the road in the next 6 years, which is a pretty massive undertaking. And if all of that is a little abstract for you, it is easy to see that pattern via the Nissan LEAF. So the LEAF is one of the oldest electric car models available in the mass market. It was released in 2011. And every couple of years, you'll see in the chart that prices either go down or range improves, or both. And both of those things are directly connected to the battery prices that we saw dropping historically over the last decade. So what that means is consumers will be able to travel much further with their electric cars and pay less for them, which is really the crux of the battery issue, is trying to find a good price point where people will buy them, but also have a range that's practical. And those two factors are pretty much exclusively controlled by lithium-ion technology and how good it is. And that's where all of those future savings are going to come from. Not the powertrain or the motor, but just the battery itself. So you may be wondering, why are these batteries so expensive? Because seemingly we have a glut of lithium-ion batteries because of our cell phones and laptops and e-readers and tablets. Lithium-ion powered devices are everywhere. So why are they so expensive when it comes to cars? The reason for that is the battery capacity of all of the devices that we use on a daily basis is incredibly tiny compared to what electric cars need. So an average smartphone has a capacity of about 0.0055 kilowatt hours in its battery. It takes about 1 kilowatt hour to charge a smartphone for an entire year. If you compare that to an electric car, it is thousands of times more energy intensive in order to power that car. So really, even though lithium-ion technology has blown up because of all of these devices, our demand so far has been pretty small compared to what growth we can expect because of electric cars. And another reason why these batteries are expensive is because the supply chain between battery manufacturers and car manufacturers has not developed. So a lot of cell phone manufacturers or device manufacturers actually control their own battery supply. But with the advent of electric cars, we're actually seeing a need for two industries that have previously been totally unrelated to have to come together and make these new connections and partnerships. In the past, car makers have always been able to control how many engines they can produce in a given year, but all of a sudden, it's out of their hands. Then finally, the raw materials for these batteries are pricey. Cobalt, nickel, and lithium are all really expensive compared to some other metals, as we'll see a little bit later. So it just makes these batteries much more expensive to produce on a large scale. So with those factors considered, why do batteries continue to fall in price? Well, part of it is with their application in electric cars. I mentioned before, the electric motor only has about 17 moving parts, while internal combustion engines can have 400 to 500. So it's already less expensive to put together an electric car because of their mechanical simplicity. And so savings in manufacturing the car and the labor that it will be required to manufacture the car will be offset against high battery and development costs. That'll actually make it much easier for businesses to produce more of these batteries. So because of the law of economies of scale, the more units that are produced, the less it will cost to produce each subsequent unit. So not only are automakers increasing their ability to build these cars, but battery producers are increasing their capacity to manufacture the packs for the automakers. So they see where trends are going. They understand that we're going to need many more batteries in order to meet this projected demand of 8.6 million vehicles on the road. So they are building out their factories. You can see that even in the last 5 years, manufacturing for lithium-ion has tripled. So it's really moving quite quickly. And then finally, research is focused on trying to decrease the use of these expensive metals so that we can save on production costs without losing out on performance. So the less that we can use of lithium, cobalt, and nickel in order to produce our batteries, the cheaper it will be. All right, I will take a short break for questions. So Chris asks, I have an EV with CHAdeMO. Can I power a 240 volt outlet with an accessory like an emergency generator? Good question. So the Nissan LEAF is actually the only car that is able to output power to a load other than its own powertrain. But Nissan is not advising that people do that just yet. So while it is technically possible, that type of technology is still being developed. And we're hoping to see more opportunities like that in the near future. MR Smith asks, do you have global numbers as well as US? Yes, so the US is actually lagging behind quite a few countries with more aggressive purchase incentives. So both China and Norway are reaching much higher numbers of sales because of those incentives. And I believe worldwide, the total number of cars available are about 4 million on the road right now. That's just off the top of my head, but I will try and get a more accurate figure to you after the webinar is over. Chris asks, Eversource promo pays for car charging stations for their customers only or everyone? So the Eversource Make Ready program allows people to be able to pay for charging. I believe they're subsidizing stations for their customers and for businesses that want to upgrade their electrical infrastructure to do so. Ken asks that DC fast charging stations are crucial, but they're expensive to build, and utility demand charges make them uneconomical at present. Is there a solution? Yeah, so I would say that DC fast charging is going to be really important for people who are making longer trips or need to charge quickly to be able to drive hundreds of miles in a day. But for most people, simply plugging in more often will be able to meet the charging demands of folks without having to invest in as expensive infrastructure. So just by kind of changing the paradigm for how we charge will help with that. And happy to talk a little bit more about that offline. Mark Holman asks about the global supplies of key metals, which I will put a pin in because we'll talk about that in a little bit. And we have a question about Tesla producing batteries. Again, we'll talk about that in the next section. Kim asks, some EVs have thermal management for their batteries. Has this increased performance significantly? So I'll say all lithium-ion batteries need to be operated at a certain temperature in order to be maximally efficient. So all EVs have these thermal management systems. And I wouldn't say that this improves performance so much as it maintains performance. So it allows the battery to continue to have a long life and get the most out of them. All right. Okay, so that's all I see. Thank you for those questions. And again, I will try and put together some more complete answers offline. So, to the question of mining. Not only is there an economic incentive to remove expensive metals from the batteries, there is an environmental and human rights incentive as well. And I noticed that there were a lot of questions coming up about this issue of mining because it is a very important factor in the battery production process. I will say there are really important differences concerning how each metal is mined. It's not just one unilateral process. And so the challenges of each one is unique. There are mining facilities all over the world to be able to meet the demand of these batteries. Particularly, there are large lithium deposits in Chile, and so they are becoming a major player in producing these metals, but also in other parts of South America and Asia as well. We know that lithium mining, compared to lots of other types of mining, requires water because the lithium basically is mined out and floats to the top. And so having to deal with the amount of water that is required will continue to be a challenge for these miners. On a totally different scale, on the other side, is cobalt. So cobalt is mined artisanally, as it's called. So people go out and basically pan for it. This is mostly done in the Democratic Republic of the Congo, where about 60% of the world's global cobalt comes from. And so there is an issue of labor there as well, because people are exposed to unsafe conditions, and high exposure to cobalt can make people sick. And so these are issues that we're seeing, notwithstanding of electric cars, but just with our current our current cell phone and tablet battery demand, these are issues that are already existing. But our hope is that economic pressure, so trying to reduce the cost of these batteries, will continue to help alleviate these issues and reduce dependence on mining. So someone had asked earlier, what to do about the limited resources that we have in relation to lithium and cobalt. And the answer is that all of the resources that we have are finite in some way. Fossil fuels are finite, these metals are finite, and so part of the challenge in creating sustainable processes for electric cars will be to reuse and recycle the materials that we already have. And so recycling presents a great opportunity to be able to reduce our dependence on mining and not have to mine as much. So unfortunately, as it stands, about less than 5% of lithium-ion batteries are currently recycled compared to nearly 100% of lead-acid batteries. So part of the problem is that the existing process we have to recycle batteries is energy intensive and expensive. So lithium-ion batteries, in order to be recycled, have to be smelted. And you can't really recover all of the original metals in the battery through smelting because you're basically using the different melting points of each metal in the battery to be able to separate them. So while you can recover cobalt, nickel, and copper, things like lithium, aluminum, and plastics in the battery will be burned in the process. And so just trying to manage that and get the most out of recycling is quite difficult, also because toxic byproducts are created every time you smelt, and so managing that is quite difficult. Lithium is also pretty reactive, and so if it's disposed of improperly, it can ignite, which presents a safety issue for any type of recycling facility that would be specializing in this. And so a process would have to be designed to avoid this and make it as safe as possible. And then finally, another challenge that we have is that, as we discussed earlier, there are all different types of battery chemistries and different ways that each battery pack is assembled. And so in order to be financially feasible, the process would have to do something different for each battery. It's not a one-size-fits-all type of process. And there's no standardized way to take them apart and reuse the components in a way that's profitable. And because this economic model for large-scale recycling just doesn't exist yet, battery producers are not focused on improving recyclability. They have a lot of other factors to be considering when doing battery research. Recycling is just not at the top of the list. But that being said, economic pressure is an effective tool. And so by 2025, when we are expecting to see those 8 million EVs on the road, it's possible that cobalt from recycled batteries could make up to 20% of demand. And so there is hope, but the recycling stream is just moving very, very slowly right now. And part of the reason for that is we want to be able to develop batteries in a way that's innovative and encourage battery producers to find new ways to create the best technology. And so we don't want to close the door on these developing technologies, and we don't want to close the door on the potential for reuse as well. And part of the reason we want to think about reuse is that these batteries last a long time. So in general, batteries do degrade the more that they're used, and that's done because they lose charge little by little over a long period of time. So this is something you've probably noticed in your smartphone. So the longer that you have your phone, the more that you charge and discharge it, it won't hold as much of a charge as it did when you first got it. And again, that's caused by frequent cycling, not age. So the more you plug in and use and plug in again, that'll generate more heat within the battery, and that'll cause less of its storage capacity to be available in the future. But even with this kind of unavoidable natural process in the battery, we are seeing really, really long lifespans. And so in the graph here, you'll see that this is an example of a Tesla Model S battery that are losing capacity over time, but it's really manageable. So a lot of these cars have ranges above 200 miles, most of them in fact, and they only lose about 15 to 20% of their capacity throughout their lifetime. So for cars that are going over 100,000 or close to 200,000 miles per hour, we will see continued positive performance. And we like to say that for folks who are a little concerned about their battery lifespan and performance, it is almost guaranteed that batteries will last the life of the car. But if they don't, and if something unexpected were to happen, EV batteries come with a warranty, usually 8 years or 100,000 miles, if the battery loses more than 20 or 30% of its original storage capacity. So for people who do experience a kind of issue with their battery, it's easy to replace with no out-of-pocket cost. So in terms of the battery technology, these batteries will last quite a long time, which is a good thing, because after a battery is done being used in a car, it will continue to be valuable even after the car's life is over. So as I mentioned, a battery is considered to be significantly degraded if it's lost about 20% of its original capacity. So if a 60 kilowatt-hour battery is acting more like a 48 kilowatt-hour battery, that might not be great for a car, but it's still a significant amount of viable battery capacity. And so instead of sending it straight to the recycler, it has great potential for reuse. And this will be effective even as we develop a recycling stream for the technology that we have. And grid storage in particular presents an incredible opportunity for used EV batteries. So since electric cars are powered by energy from the grid, more renewables will mean cleaner running electric cars. But because we can't control how much solar and wind are produced at a given time, we can't make the wind blow harder or the sun shine more fiercely. We need a way to be able to store energy created at one time for use in the future. So why not rely on used electric car batteries to meet the storage demand? It's really a match made in heaven, and that's the direction that we're going in. So Daimler, the German automaker that makes Mercedes-Benz, took used batteries and actually were able to turn them into a stationary storage project. So these were batteries that weren't good for cars anymore because they had been used and the cars had reached the end of their life. But now the batteries can store energy and feed back into the German grid at a rated power capacity of about 9 megawatts. So that is pretty sizable, considering that these batteries had reached the end of their useful life in cars. And just to put the cherry on top, the project is housed in the retired coal plant. So you're seeing this incredible transition to be able to both make electric cars run more cleanly and also support renewables on the grid. But that's just one example. There are so many potential reuse projects that could be used. So one other one could be, as someone mentioned, using their electric car battery, whether it's still in their car or has been removed because they got a new car, to support their home in the event of a blackout. So using these batteries as stationary storage for a home instead of the grid. Another example could be what Japan has done with their off-grid streetlights. So they've basically just taken used Nissan LEAF batteries, attached a solar panel and then a couple of LEDs to them, and then all of a sudden they have off-grid streetlights, which will continue to provide light even in the case of a blackout. So we can see that these batteries, in addition to offering opportunities for storage contribute to our resiliency as well in the face of blackouts. I will take a brief pause for questions before we move into our last section. Kate asked, will we be able to have a new battery installed in an older EV to increase efficiency? So that is certainly possible. That's definitely something I would like to see, so that we can continue to reuse good resources instead of developing energy and cost intensive processes to recycle them. Right now, there are not enough EVs to be able to run those kinds of projects, but I think in the next decade or so, those kinds of possibilities will definitely be opened up. So someone's asking about the Tesla Powerwall and how we expect to have incentives change in the future. So that's a good question. That's probably more of a policy question. But right now, utilities are working on trying to develop grid scale storage projects because they're easy to manage. So with grid scale projects, it's easy for the utility to see what resources are available to them at a given time, and then be able to dispatch them as necessary. Moving forward, I think when more people are interested in using used EV batteries or existing EV batteries as storage, there will need to be a way for the utility to dispatch those resources. So control them in a way that increases the reliability of the grid. So I'm not sure exactly what incentives will be available, but these are definitely projects that utilities are considering as they move forward, because it definitely benefits them as well as the homeowner. So Steve asks, how do you get to the batteries in an EV? So the answer I would say is you probably don't want to touch it. EV batteries are very high voltage, and so you'd really want a licensed mechanic to be able to take a look at that. But in the future, we expect for people to be able to control how their batteries are used in more variable ways. So the idea would be that you can plug in your car and use it as backup storage for your home, but that relies on technology that is still being developed. So for right now, consumers are pretty limited in how they can use their electric car batteries, but those technologies are coming. All right, so have some great comments here, but we're running out of time. So I will move on to our last little section. So returning to the question of electric cars, I said to expect over 8 million EVs on the road just in the United States by 2025. And so there is this logistical question of, will automakers have access to enough batteries to be able to produce these cars that everyone is wanting to buy? Because we do have a lot of stakeholders in the process. We have car manufacturers, we have battery manufacturers, we have the mining companies, and so we need to be able to scale up production quickly to meet the demand. I'm sure many of you are familiar with the slower than expected rollout of the Model 3. They just could not produce enough cars to meet the demand that they were seeing last year. And so it does indicate that there are a lot of moving pieces that have to be in sync in order to create an effective supply chain for electric cars. The Tesla Gigafactory is an attempt to circumvent the difficulties of those supply chains by putting it all under one roof. But basically, the Gigafactory is it's a Panasonic factory. They produce batteries to put in these cars. In theory, the factory was supposed to produce about 35 gigawatt hours of batteries per year, but it only achieved around 2/3 of that, which is why Tesla failed to deliver as many Model 3s as they thought they could earlier in the year. And so the question of, are there going to be enough batteries is a serious one, and this problem is not unique to Tesla. Because battery manufacturing has to scale up very quickly in order to meet the demand that we're forecasting. So more and more partnerships between automakers and battery producers are happening because both organizations want to lock down supply. So as an example, Volkswagen, which is trying to electrify all of their cars in the next decade, is working with an unnamed partner and spending over $1 billion to produce battery packs near its headquarters in Germany. And that's not shown here, and this map is just a year old. So every day we're expecting more partnerships and more automakers to try and secure their battery supply. But if you do take a look at the map, the black battery symbols represent the generating capacity in 2016, and the green represents capacity for production by 2020. So we're going to see a massive scale up in battery production just in the next couple years. And currently, there are only a handful of battery manufacturers that can meet this demand. And so wherever these factories are going to be, that's going to bring a lot of economic opportunity to those areas. And so you'll notice that China is really taking the lead on this industry because they're making aggressive moves to not only create a large market for EVs, but also create a large supply of these batteries. It's worth mentioning that China has one of the most aggressive consumer purchase incentives in the world, in part to deal with their air quality issues. And so they have been able to really rapidly scale up the amount of electric cars that are available to them. They also have several Chinese versions of Tesla. So these are automakers that are specializing in creating electric cars. And while it doesn't look like these car makers will be producing cars and exporting them to the US anytime soon, China is really setting itself up to be a global leader in this industry. And it's very likely that a lot of batteries that are going to be put into American electric cars will come from China. So finally, to conclude, it's pretty clear lithium-ion technology is going to dominate the auto manufacturing industry in the next decade. Lithium-ion batteries are crucial in order to get the amount of electric cars that we need, and we're expecting a total transformation of the industry. And while we expect that these batteries will be good enough to last the lifetime of cars that we're using them for, there are certain things that you can do to be kind to your battery and get the most out of it. So these are tips that, for the most part, can be applied to lithium-ion technology, whether it is in your cell phone, in your computer, or in your car. So the first tip is, don't let your device sit with a full battery. So lithium-ion batteries tend to self-discharge if they're stored at 100%. So basically, what's physically happening is those lithium ions over in the negative part of the battery creep over to the positive part, even though there's no applied load, which makes these batteries lose capacity faster. So if you know you're not going to be using your car or your device for a couple weeks or months, just set it or charge it to 50% and then shut it down and leave it that way. Some cars you can leave plugged in and set as a maximum charge level of 50% so that it doesn't take on any more charge than that. Another technique that you can use to expand the life of your car is using the top-off model for charging. So most people who are used to driving a gasoline-powered car are used to the paradigm of driving until their tank is almost completely empty and then refilling it all the way to the top and then repeating the process over and over again. But these kinds of full discharges will make the battery degrade faster. And so in general, by keeping your battery between a happy 20 and 80% of capacity, most of the time you'll have enough charge to do your driving and you'll be doing something good to your battery. And one way to do that is to just charge more frequently for shorter periods of time. So plugging in when you can. The third tip is try to rely less on fast charging. So again, degradation happens from that frequent cycling. So if you need to rely on fast charging for a road trip every once in a while, it's totally okay, but try to limit your use of it to just long distance driving or emergencies. It's much easier to just plug in your car conveniently, opportunistically when you can, and that will significantly improve the lifespan of your battery. Then the last tip is to try and avoid extreme temperatures. So when you can, keep your car parked in a garage when it's cold outside or in the shade when it's hot outside. So the less that you can expose your car or device to extreme temperatures, the better it'll fare. And again, these are tips that you don't need to follow religiously to get the most out of your battery, but if you're diligent, then it can just make sure that you get the most out of your device. And I will just say anecdotally, since applying some of these techniques to my own cell phone, I don't drive a car just yet, but I have noticed a significant better performance in my personal devices since following some of these tips. So it's a good thing to do to take care of your devices, but there's no reason to believe that electric cars won't last the life of the car. So that is what I have for you. I know that I covered a lot of information in this webinar, so I do thank you for joining me today. I hope you got something out of it. And I will review some of the lingering questions that folks had and be sure to get back to you in an email at some point later this week. So I thank you for participating, and if you are interested in asking a couple of more questions, feel free to stick around. But otherwise, thank you so much for joining me today. So looks like Steve asks, are there new battery technologies that will be better than lithium-ion batteries? So most likely, yes. I didn't have the opportunity to talk about it today, but in addition to improving the lithium-ion battery, there's plenty of research being dedicated to other types of chemistries that are expected to be even better. But because of the slow rollout from the lab to wide-scale manufacturing, nobody really expects those advanced technologies to make a difference in the next decade. And at that point, lithium-ion may have already dominated the market to the point that it might not make sense to transition to a new technology in the near future. So maybe in the next couple of decades, we'll see better technologies, but lithium-ion will carry us in the next couple of years. Steve also asks, does the battery pack play into the acceptance rate of how much energy can be transferred into the car? So no, actually, that is a totally unrelated device that is in charge of that. So there is an onboard charger installed in every electric car, which manages how quickly the battery can accept a charge. And so that is the device that will affect how quickly you can charge. I do have a blog about that available on Green Energy Consumers blog if you're interested in that and reading up on that a little bit more. Ben asks, the tip to not let the car sit with a full battery is huge news. He usually does exactly this. Yeah, so I would say if you can avoid charging to 100%, then that's generally a good idea. I mean, obviously, if you need to charge your electric car to 100% in order to drive the amount of miles that you need to drive in a given day, then that's no problem. But in general, if you are the average commuter and you're only going about 40 miles a day, then there's no reason to have it charged to 100% if you can avoid it. But again, it's not mandatory. So if it makes you feel better to have your car ready to go at a moment's notice, then it's really not a problem to do so. But in terms of just maximizing utility, it might make a difference. Mark asks, how can I avoid my Volt from using gas to warm up the battery in the winter? So I'm not sure exactly at what point the Volt starts using gas to keep the battery warm. But one thing that you can do is called preconditioning your vehicle. So that means if you keep it charged or plugged in at night and then turn it on in the morning, it'll actually use some of the energy from the outlet to keep the battery warm. So if you can, keep the car plugged in overnight, and you should wake up and be ready to go with a warm battery the next day. Okay, those are all of the questions that I see here, but again, do not hesitate to reach out to me via email or phone if you would like to continue to ask questions or have some points that you would like clarification on. So thank you very much for joining me today, and have a great rest of your day.